Hello everyone, my name is LUCA PIZZIMBONE and this is the presentation for the IBM Coursera Advanced Data Science Capstone. As per course requirement, there are two parts of this presentation. The first is a one high-level presentation which is assumed to be prepared for stakeholders, while the second part will be a peer-to-peer review presentation where we can have a look together to more detailed information on how data have been explored and transformed, how feature engineering has been conducted, and models defined, trained, and evaluated. Of course, I'm also inviting you to have a deep look at the 6 notebooks, Jupyter notebooks with the complete code of the project that have been shared with my classmates in the Coursera website. Okay, let's start now with the first part of the presentation, the one dedicated to the stakeholders. Stay tuned. In this presentation, we will look at project scope, dataset, use case, and solution to the use case. The project explored the possibility of energy forecast based on historical smart meter readings and weather data. We assessed the following algorithms, which are linear regression, gradient boosted trees, and random forest for machine learning algorithms, and LSTM, long short-term memory, for deep learning algorithm. The analysis includes all the following topics, which are impact assessment of extra features on top of basic features, cross-validation and grid search for hyperparameter tuning, comparison of the performance for all analyzed model. The dataset that I used in the project is a public database of smart meter records of electricity from London area, UK, which is available at the website of kaggle.com. To better follow the energy consumption, the government wanted energy suppliers to install smart meters in every home in England, Wales, and Scotland. There are more than 26 million homes for the energy suppliers to get to, with the goal of every home having a smart meter. This statement is together with the data supplied in the website, and it's showing the importance of using smart meter in the next future, especially when there will be electrical vehicles and renewable energy. The used available data are the following. Daily energy consumption, smart meter records of energy consumption, daily summary for about 3 years and a quarter. Daily weather data, which are taken by Dark Sky API and UK official bank holidays to distinguish working and not working days. Let's have a look at the main data set in this presentation, which is the daily energy consumption. What we notice at first is that the number of smart meter is actually growing, so it's not constant, and this made necessary to normalize the energy consumption by the number of smart meters or households. So then we have a kilowatt hours per household as our target in this project. We can notice also that the last number, so the last smart meter, has only one energy count, so it's much smaller than the other. So that could be due to the fact that they download data before the end of the day, for example, or any other reason. But this data is not suitable for us, so we will remove this data. So the use case is the prediction of energy consumption 24 hours ahead, which is very useful for the electrical system operators so that they can optimize their generation resources and related cost, and of course without impacting the power quality and security requirements of the grid. This prediction will be even more important in the energy transition phase, which are living today. This energy transition, it means that there will be much more and more renewable energy in the system, and also consumer are becoming prosumers. So it means that there is no more only consumption of electricity, but also production of electricity from the customer of the system operator. For example, by photovoltaic, by wind turbines, or any other source of generation. In this use case, we would like to predict the total energy consumption of a full day ahead based on available smart meter reading and weather data. In this slides, we can see this use case. We have here it's called actor in UML diagrams for use cases. That is will run the Jupyter notebook, and this Jupyter notebook include also creation of input data from weather and smart meter data, and optionally the update of the model training that can happen maybe once every 6 months or once in a year. When we have new data, it will be a good idea sometimes to times to update the model training. So the Jupyter Notebook also will help to select the best performing model, and finally to predict the energy consumption, which is our target. In this Jupyter Notebook, we evaluate different models. The first, in this table, we have the results of each model. The first is a linear regression with basic features, which we have the score for the train and test data, and we have a quite clear overfitting in this case and not so good performance here. But as far we add extra features based on smart meter data, this R square meter is really boosting up and become almost very similar from train data and test data. So with very good results already with a simple linear regression. And then we tried also two different algorithms, which are gradient boosted trees and random forest, and we guessed these kind of results. So what we noticed that the gradient boosted tree has a very good result in train data, but not very good in test data, so there is overfitting. And then we decide to do a cross validation for gradient boosted trees to see where we can improve the performance on the test data. And from 0.88 we rise up to 0.91, which is much better, but still maybe there is still quite a discrepancy, and the random forest is still performing better even without cross validation. Finally, we evaluate the LSTM, which is the deep learning algorithm, and we got definitely the best scoring with 0.97 and 0.96 respectively for train and test data. And seems to be a very good result and also quite a balance between train and test. In these slides, we see the actual versus prediction values, and these are the results for the LSTM model, so the selected model, and we see that they are relatively good. We see also the mean absolute percentage error, which is equal to 1.927, and the actual percentage error for each sample, where we can see that the maximum was a little bit higher than 10%, but still lower than 12.5% for a few points. This is the end of the first presentation, and now we continue immediately to the peer-to-peer presentation, where you can have a little bit more insight in the data, in the model, and the evaluation. In particular, we will see the architectural choices that we did, the data quality assessment, data preprocessing and feature engineering, model performance indicator, and model algorithm. The architecture that we used in this project, we have an implementation in a local machine, in this case in the laptop. In the execution environment is the Conda environment with a Python 3.7.11 plus Spark 3.1.2, and here we have 6 Jupyter notebook for energy forecasts, data exploration, um, extraction, transforming and loading, feature engineering, model definition, training, and model evaluation. The interface between this execution environment and the data file is through the local disk drive. This is necessary to exchange data from one Jupyter notebook to the other one. A better alternative for architecture would be they use the IBM Cloud Server with Watson Studio environment with Python 3.7 and Spark 3.0. We have exactly the same six notebooks, but the only difference is that the exchange of data now is with IBM Object Storage, which allow also the use of file from one data from one notebook to the other one. Let's have a quick look at the technologies that we used in this project. For example, the data source was CSV files, and we do exploration with pandas. So for data integration, as we said, we use a Jupyter notebook within Python's and Spark Conda environment, and we use it for data integration. Especially, we use it only pandas because it was quite flexible and was enough to handle for handling the data. The data repository, we use the local disk drive, but as alternative, the IBM Object Storage would be also a very good solution. For discovering exploration, also we continue to use pandas because was good enough also for feature engineering. But when we go to actionable insights, then we switch it to TensorFlow and Keras for the deep learning model and Spark for the machine learning model. Finally, all the data product finally are the six Jupyter notebooks that can be used for the prediction. We see again now, like in the former presentation, the data, but additionally to the daily energy consumption that we already discussed, we have a look also at the other data, which are weather data. We see that it's very difficult to read this long data frame, so I summarize here in the bottom left the name of the column, and we see that we have plenty of data from weather, but some of them they are very correlated each other, and some were not really interested. So at the end, I selected at least five kind of data that can be of interest as features, which are temperature, I say probably max, but also we are going to select max and minimum for to be on the, yeah, maybe on the safe side or not. Dew point, humidity, pressure, and cloud cover. And then finally, we have also UK bank holidays, which is a list of bank holidays for the 3 years that are data provided. So let's see the summary of the findings for this data exploration. So the first point was smart meter. They were not constant, so they are changing with the time due probably to the implementation phase. So we had to normalize the number of the energy consumption with the number of household. The date format of the three data frames that we had to merge together was not the same, so we had to do some manipulation of the data to get the same format of the date so that we can merge together in perfect matching of the data frame. And also there were a few missing value and one incomplete value, so we had to eliminate this small value for to have more consistency in the data. Have a look now to the feature engineering part. These are the basic weather features, and what we did here is to plot at first these features with possible features in a time dependent diagram where we have the energy household, the blue curve, and the red and yellow is the temperature maximum minimums, and we clearly see a kind of dependence because when one is growing, the other is diminishing. So that means that, for example, when the temperature is going down, maybe electric heaters they are turned on, so that we have much higher consumption. So in principle, we see there is a clear dependence of this part. The same we can see for this is a humidity. In this case, when humidity is growing, electricity consumption is growing, and so on. While it seems to be not very high correlation between visibility and energy consumption, and this is, it seems quite a noisy correlation. Yeah, not really correlation. But very interesting is daylight duration. So in this case, by using the time of sunrise and sunset, we calculated the day duration during the year, and we see in fact that there is a correlation. So when the day is shorter, there is more electricity consumption, probably for light use, for example. That could be a correlation. And also we see a correlation when we see the difference, for example, between working day and not working day. There is a slight difference in the statistic of consumption. So in addition to this basic feature, for which we calculated already the performance of the linear regression model, we added new feature engineering features, which are energy statistic for 1 day, 1 week, and 1 month before the actual value, and these values are taken directly from the smart meter reading. This is the line of code used in the Jupyter notebooks, and you can find here where is the function that is defining these new features. So basically, um, we created on the base of the historical data this new feature. Now we summarize here the correlation plots where we see the correlation of the basic and extra features with the energy average, which is our target and which is also the first line indicated here, which is 1. So we see that we have some high correlation related on the weather side, but also very high correlation in the extra features. So we used both cases and of course combine it together. So we created two different data frames using the pipeline of PySpark, and in this case we create a vector assembler, and also we normalize data with a min maximum scalar to get similar values from 0 to 1, so in the same range for all the features, so that we don't have a predominance of one features on the other, because maybe the value they are given a different in different scale. So the vector assembler 1 has only a limited number of features, which are related to weather data, day duration, and working or not working day, while the other dataset has much more features, including the energy statistic, 1 day, 1 week, and 1 month before the actual data. Finally, we saved the data in the Parquet file so that we can use the data in the next notebook. How we evaluate the performance of the models. We used the R squared because it's a regression problem, and R squared is suitable for regression problem. And also we have it's quite simple to use. It's the value range from 0 to 1. And 1 means that all variation of the dependent variable are completely explained by the movement of the features, and 0 that there is no, it cannot explain any, so the variable they are completely independent. There is a risk in using R2 when we have a large number of features, because R2 always increase with the number of feature, also in condition of overfitting. And that's for this reason, to avoid this problem, we monitor both train data and test data. And also we don't believe it will be really a problem, because the number of feature is still much lower than the number of predictions that we estimate for this with this indicator. However, at the end, for the best performing model, we also calculate other performance indicator, which are the maximum error, the mean absolute error, the mean squared error, and the mean absolute percentage error, so that we can have a better view of the performance. Now we have a look very quickly in the model definition process, because we have a combination of 3 machine learning model and 1 deep learning model. So at the beginning, we started with the linear regression model and we tested it with the basic feature and extra features. And then for the best performing, in this case, the extra features, so we are going in the lower part of this activity diagram. We follow this lower branch, so we used extra features to evaluate other regression model, which were gradient boosted trees and random forest. Then we used the cross-validation for the best performing model for the non-deep learning model, but also we add a deep learning model to compare together, and then we select the best one, the best performing model, and for the best performing model we add the calculation for additional features. So with this model process we avoid, let's say, too many combination, but still having good results and having some pre-selection of yeah, of performance. So let's have a look at the model algorithm for the cross-validation of the gradient boosted trees. So we used a parameter grid data where we see the three, in this case, 3 parameters that have been tuned. We have the max depth, max bins, and maximum number of iteration for the gradient boosted trees regressor. We set a list of parameters that we want to test, and then we used R2 here as a metric for evaluation, and we used the 5 folds. That means that the training data have been divided in 5 folds for cross-validation. 4 of these 5 of the training data is considered as actual training data, and the remaining 1 fold as validation data. And this has been repeated several times until all folds has been in the role of validation data. For the hyperparameter tuning for the LSTM, I defined a function where I'm passing to this function some of the hyperparameter like batch size, epochs, number of epochs, and the loss functions. So we have a list of this parameter, and with 3 different for loops, I'm going to investigate all the combination, and then in the all the models have been finally saved in one folder that has been loaded in the other notebook, which is going to select the best performing model. And now we come to the evaluation, and we see the same table we saw in the previous presentation. In this case, in this presentation, I add also additional diagrams where we show the prediction for other models. So for the first model, which has not very good performance in the test data, and see 0.68, and see that is clearly, let's say, it's a clear less performance than others. In the number 2, we see the linear regression with the extra features, and we see how the extra features they can really improve the performance of the model. And finally, in the number 3, which has the best performing R squared in the test data, we see the prediction is even better. For this model, the LSTM, we also calculated, as mentioned before, the max error, which is 1.3, the mean absolute error 0.2016, mean squared error 0.0749, and the mean absolute percentage error, which is only 1.927, which is a good, quite good result. In this last plot, we see the error percentage for each point of prediction, and we see that the maximum value here there are above 10%, but below 12.5%. There's only a few spots, but the average, as we said before, the mean is 1.927%. Now we are at the conclusion. So the use case was to find a model suitable for prediction of energy consumption based on smart meter data and weather data. We considered three machine learning models, linear regression, gradient boosted tree, and random forest, and one deep learning algorithm, which is long short-term memory. We defined the models and tuned them by using feature engineering, grid search, and hyperparameter tuning. We compared the performance of all the models by using the R-squared meter, and we compared the prediction versus actual values by plot diagram, and the best performing model was the LSTM with hyperparameter tuning. Finally, we assessed further performance meter for the best performing model, that was the LSTM. Thank you very much for following this presentation. Goodbye.